I have 30 students in my class who've each taken a maths test, and these were their results. I need a way to summarize these results. In other words, I want to use as few numbers as possible to convey how well my class did on this test, whilst maintaining as much information as I can. One obvious way to summarize the results is to calculate the mean or average, where we add the scores together and divide by the number of students, in this case 30. I'll write the mean as x bar. We might also want a way to summarize how spread out the scores are. Did the students all score very close to 53.3? Or did some students score much higher and others much lower? In our example, we can see that the scores vary quite significantly, so their spread should be relatively large. One idea might be to use the average of the differences between each score and the mean. But if we do this, then the students who scored worse will cancel out with those who scored better, and this will always give 0. Maybe instead we should take the absolute value of the difference. This is the average distance of each student from the average score, and this measure of spread has a name. It's called the mean absolute deviation. The only problem with it is that absolute values are very difficult to manipulate. There is another way we can ensure that each term of the sum is positive, that is by squaring them. And we call this the variance, which I'll write as sigma squared. This has the advantage of being able to expand out the brackets, which makes it much easier to manipulate and discover new facts about the variance. For example, if I have two different sets of data, x and y, then I can use the formula to find the variance of something like ax plus by. These are just the variances of x and y. And this term at the end has a special name. It's called the covariance of x and y. This fact about variances will be important later on. Also, if x and y are independent, meaning they have no influence on each other, then the covariance is 0. Now that I've hopefully justified that variance is a natural thing to use to measure the spread of data, let's go back to our original problem. Carrying out this calculation here gives an answer of 234.82. Square rooting the variance gives something called the standard deviation, which in this case is about 15.3. But in this video, we're focusing on the variance. So why did I say in the title of this video that variance is a matrix, which is a grid of numbers? Clearly, this is just a single number. Well, to see the variance matrix, we'll need to look at a slightly more complicated scenario. So let's go back to my class of 30 students. And this time my students have each taken not only a maths test, but a science and an English test too. Instead of assigning each student a number, I'll need to assign each student a list of numbers in the form of a vector. And instead of writing 90 numbers on the screen all at once, I'll share a plot in 3 dimensions of the students' results over these 3 tests. Each black point represents a particular student. Our task here is the same as it was before. We want to summarize the test results using just a few numbers, whilst conveying as much information as possible about the original data. First, how should we calculate the mean? We could add all of the test results together. 30 students with 3 tests each is a total of 90 tests, and divide by 90. And this would give us a single number, the average overall test score. This approach, though, loses some valuable information. For example, which test the class performed the best on overall. A better approach would be to add the 30 vectors together and divide by 30, and this would give us an average vector, which I'll draw as a red point on the diagram. The components of this vector are just the average scores from each test, allowing us to compare them. We can see that the students overall did the best on the English test with an average of 60.9, and worst on the science test with an average of just 51.2. What about the variance then? Should it be just a single number telling us generally how spread out these black points are in 3D space? Maybe the average of the square of the distance from each black point to the central red point? Or the components of our mean vector are just the means of the individual tests, So maybe our variance should also be a vector, consisting of the variances of each individual test. This carries more information than a single number, but we're still losing lots of information here. Namely, we're losing information regarding how the test scores relate to each other. If I look at the test scores top down, we can see that there's a clear correlation between the maths and the science scores, which is to be expected. If instead I look from the front, we can see that there's not so strong of a correlation between the maths and English scores. And likewise, if we compare the science and English scores from the side, there's not a very strong correlation here either. The way we'll end up capturing these relationships between pairs of variables, that is, whether they have a strong or weak correlation, is by using the covariance. But before we get ahead of ourselves, I want to take another look back at the idea of representing the variance as this vector. What information exactly is this vector actually conveying? The variance of the math scores, being 234.8, means that if I project each of the points onto the maths axis, the points along this line are simply the students' math scores. The variance of the points along this axis is 234.8. Similarly, we could do the same thing for the science and English axes. If we want our measure of variance to capture the shape of the data overall, we need to capture the variance in every direction, not just along these three axes. This means it should encode the variance of the data when it's projected onto any arbitrary axis. For example, when I project the data onto this axis, we get points which are relatively spread out. If instead I project onto this axis, we get points which are much closer together. This happened because of the linear correlation between the maths and science scores. The maths and science scores lie approximately on a straight line, which means when I project data onto the axis shown here, which happens to be perpendicular to that line of best fit, the data ends up very close together and we get a small variance. If we can find a way to determine the variance of our data when projected in any arbitrary direction, we will have encoded how spread out the data is overall, but also how the different test scores relate to each other, and this is exactly what we need. So here's a simplified diagram. The green line represents the axis onto which we will be projecting our data, and the black point is one of those pieces of data, let's call it X, consisting of a maths, science and English score. This point X can also be thought of as the vector going from the origin to the black point. Let's say the line is in the direction of some unit vector u with components p, q and r. Unit vector means that the length of this brown vector is 1. We want to find out how far along this green line the black point will end up once it's been projected. When I say project, I mean we're going to find the point on the line which is closest to the black point. This is the point where this red perpendicular intersects the green line. I'll label the point we're looking for in orange. I've also labeled the length of the blue vector as the magnitude of x, and the length of the brown dashed vector as the magnitude of u. We need to find this distance from the origin to the orange point. Luckily, this is quite easy with some basic trigonometry and something called the dot product. Don't worry if you don't know about dot products, it's only one small step. Let's first label the length we're looking for as a. Using some high school trigonometry, cos theta equals a over the magnitude of x, where theta is the angle between the blue and the green. Notice that theta is also the angle between the blue and the brown, that is, the angle between the vectors x and u. We can then use the dot product to find the angle. The dot product of two vectors is equal to the product of their magnitudes multiplied by the cosine of the angle between them. We can then substitute cosine into this, and then since we said that u is a unit vector, meaning its magnitude is 1, x dot u equals a. We found the length that we're looking for. Remember, we want to determine the variance of our projected points, how spread out the data is, after it's been projected onto this arbitrary green line. We want the variance of x dot u. Recall that the components of x are maths, science and English, and the components of u are p, q and r. You can compute a dot product by multiplying the corresponding components and adding the results together. Now we can use that fact from before about adding variances, or at least a slightly more complicated version of it. And we get this quite messy looking formula. Earlier in this video I showed you where this result comes from in the case of 2 variables. This 3 variable version isn't much more difficult to come up with, it's just a little bit more messy. Now we could leave this as our final answer. This formula will tell you the variance of the test scores when you project them along an axis, which points in the direction of a unit vector with components p, q and r. But of course it would be much nicer if we could somehow separate the p's, q's and r's away from the m's, s's and e's and keep everything separate. We can do this with some reordering and smart factorization. We start by reordering the sum, so that in each line we have a common factor which can now be taken out. Notice that now I have p times something plus q times something plus r times something. We can rewrite this then as a dot product. You might also notice this nice repetition of p, q and r. And those of you familiar with matrix multiplication might notice that we can write this as a matrix multiplied by a vector. Then also notice that this vector pqr is the direction vector u we defined earlier. The matrix in the middle contains no p's or q's or r's. It's entirely independent of the axis that we're choosing to project along. It depends only on the data itself. To find the variance of my data along a particular axis, I can simply define u as the unit vector in the direction of that axis, calculate this matrix from the data alone, and then perform this computation on screen. The matrix encodes the variance of our data in every direction. So we define our variance, capital sigma, to be this matrix. Notice this matrix is symmetric, so we don't actually need all 9 numbers, we could just use 6, where it's implied that the bottom left 3 elements are the same as the top right 3. The variances along the diagonal of this matrix tell us how spread out each individual test was, and the other 3 elements, the 3 covariances, tell us how the scores relate to each other. Returning to our original set of data, we can compute the variance matrix by simply calculating the variances of each test and the covariances between each pair of tests. Notice how the covariance between maths and science, 232.2, is bigger than either of the other 2 covariances. This means that there's a stronger correlation between maths and science than there is between maths and English, or between English and science. And since 106.0 is bigger than 73.1, there's a slightly stronger correlation between the science and English than there is between the maths and English. And that's why and how we represent variance as a matrix if we're dealing with multivariable problems. Before I end this video, I want to make a few announcements. As some regular viewers may know, I have a real analysis course, which is just a PDF where I go through all of real analysis. Top link in the description, by the way. But I'm also currently working on a linear algebra video course with me talking into the microphone whilst writing on a whiteboard. And that project has been delayed since I currently have a broken arm, which is one of the reasons why this video was so delayed. So keep an eye out for that linear algebra course once it releases, if you want to learn more about vectors, matrices, and much more. See you next time.